Good afternoon, everyone. Up on the screen right now is the homework from Friday. So if you remember on Friday, we were doing probability distributions. So just as a quick reminder about what that is, and we're going to take up one of these questions just to refresh your memory after the weekend there. So the idea with the distribution is really just some kind of a little table or graph showing all the possible probabilities. Right? I don't know what it is. Again, if it was just something simple like, flipping two coins, that was one of the examples, right? You could either see 0 heads, 1 head, or 2 heads, and you just write down the probabilities here. Okay, so this distribution is listing out all the probabilities, and calculating expected value is kind of like doing a weighted average, right? It's just each thing times its probability. That was a very technical picture there for you. But again, we're going to take up one of the questions from the practice work from the weekend to kind of refresh your memories of how that works. So we're going to do number 7. A game is played by rolling 2 dice. If the sum of the dice is either 2 or 12, then you win $2. If the sum is 7, you win $1. And the cost to play the game is 50 cents. So is this a fair game? So we'll start with the distribution. So we'll say, let X be the money 1, be money 1. Okay, so my possible values for X, right? I can either win $2, $1, or I guess I don't win anything if I roll anything else. So I can pay $2, I can pay $1, or I can win $0. Okay, and our other column is the probability of that happening, that my variable is equal to one of these numbers. So for $2, okay, that's rolling either 2 or 12. So that would be 2 of the options out of 36. Okay, which will reduce to 1 in 18, but we'll come back to that later. Okay, for 7, okay, there's 6 different combinations that will give you a 7, 1 in 5, 2 and 4. Sorry, 1 in 6, 2 and 5, 3 and 4, and then the reversal of each of those. Okay, so there are 6 ways in 36 to get that. Okay, and the rest of it is going to be 0. So that was 8 out of 36, so this must be 28 out of 36. Okay, so again, this is the distribution. It's just a table showing me the values. So to figure out if it's a fair game, I'm going to figure out the expected value, right? In the long run, if you played this game a lot, what would your average winnings be? So we're going to win $2, 2 out of 36, or that's 1/18. Okay, and for $1, that's going to be a 1/6. Okay, and then finally it's 0, well, times the other probability, but we know that part's going to be 0. Okay, so up here, you could run this through in your calculator. I'm going to keep it in fractions for now in the hopes that it'll come out to something nice. So we got 2, this is going to be 2/18. And that's 1/6 of the time, so 1/6 is the same as 3/18. Okay, it's not going to come out nice. So this is 5/18, which as a number would be, sorry, as a decimal, okay, about 28 cents. It's 27.7 repeating. Okay, so if you play this game a lot, then it's going to cost you, you're going to win 28 cents every time you play. So therefore, this is not a fair game, right? Because the cost of playing is more than that. It costs 50 cents to play. Okay, and for part B there, if you played the game 100 times, how much would you expect to win or lose? Okay, well, we just said you normally win 28 cents, but you pay 50. So you're going to lose 22 cents every time you play. And so if we do that 100 times, you would expect that after playing this game 100 times, you would be out $22. Okay, so that's your quick review of probability distributions, which is going to lead us into our homework quiz, which is this, based on this comic strip. Okay, so I don't know how well this is going to turn out in the video, so I'm just going to read this. So Jason says, I'm thinking of a number between 1 and 1 billion. If you guess it correctly, I'll pay you $5. If you're wrong, you pay me $1. Deal? Do you really think I'm that gullible? Deal? Make it 5 million. So if Jason agrees to the page's terms, so if she guesses it correctly, he'll actually pay out 5 million, but he's picking a number between 1 and a billion. What is the expected payout of the game? Okay, so if they play to those terms, what is the expected payout, or what's your average winnings for this game? Okay, so if you can pause the video for the moment and then come back to it after the class has had, 3 or 4 minutes to work it out and hand it in. All right, so you're back. So we're going to be talking about this afternoon is what's called a uniform distribution. And the theme for this whole week is going to be different types of distributions. So we talked about it in general on Friday, what a distribution is. And now what we're going to be talking about is some specific types that show up over and over again. So the simplest one is this one, which is called uniform. And this occurs when all the outcomes are equally likely. So all it means is that for whatever situation is, every single thing has an equal chance of coming up. Okay, which means that the probability of each outcome, so our P of x equals x, would just be equal to 1 over n, where n is the number of outcomes. Okay, which would make sense, right? If you're rolling a dice, and that's example 1 here, I'm pretty sure. Okay, there's 6 possible outcomes, so they all have a probability of 1 in 6. If you had a deck of cards and were to assign a numerical value that was different to each card, then the probability of each one is 1 in 52. Okay. If you play like Law 649 and you're going to pick one of those numbers, they each have a 1 in 49 probability of coming up. So just any situation where every single thing is equally likely to happen. Okay. So again, I'm not going to write this in the table because it'd be kind of boring, but that's what the graph would look like. Okay, so the shape of the distribution should be flat, right? If they're all equally likely, then none of these frequency bars are going to be higher than the others. Okay, which is nothing like what we did on Friday when we were rolling dice, right? They were definitely had a bit of a mountain shape to them instead. Okay, so we're just going to do a couple quick examples here. Example 2, 12 pairs of shoes from sizes 1 to 12 are sitting in a row outside a shoe store. If one pair is picked at random, what is the expected size of the shoes? Okay, so I don't need to make a table to do this expected value because I know that the probabilities are all going to be the same. Okay, and there wouldn't be much point writing that table. Although maybe, I'm going to back up a second here. We'll just write that down at the start. Right, for all my probabilities, okay, I have 12 pairs of shoes, so the probability is going to be 1/12. Okay, so for my expected value, okay, that means I'm going to take each of my possible numbers, right? So I could have a size 1 shoe, and that's times a 12th. I could have a size 2 shoe, and that's times a 12th. Okay, and so on until I get up to size 12. Now, before you grab your calculators and start attempting to run all that through, this is again going into your factoring skills a little bit here. Okay, because every single probability is the same, I don't have to sit here and multiply these all separately. Right? I could factor that out. Right? It's going to be 1/12 of whatever I get when I add up those numbers. So 1 plus 2 all the way up to 12. Okay, so to save yourself some fraction work, okay, that will help out a bit there. Okay, so the sum of all the numbers from 1 to 12 is 78. Okay, and when I divide that by 12, I get 6.5. Okay, so a couple of things to note here. Okay, I mean, one, okay, this average, right? I can't actually draw a 6.5 shoe from here. Okay, but that's okay because this is an average, right? It's the average size I would expect to draw. Okay, and the second thing, and maybe you could even go back and stick it under the definition on the previous page, right? For the expected value, okay, we had a formula on Friday, right, with a little sum symbol, the sum of x times the probability. Okay, but because the probabilities are all the same here, again, it's not really a formula you can just plug into. Okay, but the expected value of a uniform distribution is just going to be, well, it's the probability, which is always the same, times the sum of the values, which is the shortcut I took here. Right, just saying, okay, it's probability times the sum of that. So you could add that to the definition if you wanted to there. All right, example 3. A game consists of rolling a single die. You win double the value of your roll, except if you roll 6, in which case you get nothing. What is the expected value of this game? Okay, so for this one, we'll do a quick little chart. Okay, we know the probabilities are all going to be the same. Okay, I'm rolling a die, so whatever these options are, they're all going to be 1 out of 6 the whole way down. Okay, so what are my options? You win double the value of your roll, except if you roll 6. Okay, so I could win $2, could win $4, $6, $8, $10, and finally nothing at the very end. Okay, so my expected value, okay, I'm going to start with 2. Actually, no, I'm going to start with my probability. This is the shortcut we just developed in the last example. So each and every probability is a sixth, and then I just have to add up those other numbers. 2 plus 4 plus all the way up to 10. Okay. So that's going to add up to 30. Okay. So for this game, the expected value is $5. Okay, now something I'd like you to do maybe for a moment here. Again, this ties into that part C on your assignment. Okay, what do you think would be a reasonable price to charge for this game? Okay, right, the expected value is $5. That's the average amount you can win. So what should you maybe charge for this? Okay, so again, maybe pause the video for a moment, have a little discussion in class. I'll share what I think, but it's certainly up for debate a little bit here. Okay, so for me, the key thing is here, okay, the average value is $5, okay, and if I look at the list of prices, or sorry, prizes, I have 2, 4, 6, 8, and 10. Okay, I wouldn't want to charge $6 because then it looks like, right, I have 5 prizes and I break even. If I look just at the prizes and ignore the 0, it's going to look like, well, I'll break even sometimes, and there's an equal amount of times to go up and down. That doesn't seem like a great deal. Okay, because this is less than 6 already, maybe I'd charge something a little more than that, like $5.10. Okay, $5.25 maybe. Okay, so just a little bit more. Okay, so that way, and again, if the average winning is $5, if you're playing, it's not going to feel like you're losing much if you play this over and over again. Okay, so if you're designing, or say when you're designing your game for your assignment, this is something you should keep in mind, that once you know what the average winnings are, you want to try to charge a little bit more than that, if possible. Okay, so that is it for the lesson. Okay, here is the practice work that you have, or of course, you have your assignment, which is due next Tuesday, which is after the 4-day weekend for Easter. So if you haven't had a look at that yet, you might want to get started on that. We have learned most of the stuff on it at this point. There's just a few more lessons this week. All right, thanks for watching, and we'll see you tomorrow.